So thank you, Molly. The title of the presentation for this session is Axial Behavior of Bonding Reinforcing Elements in Underground Applications. So I'm Hadi Nourizadeh, a research fellow at the Center for Future Materials. So I hold a Bachelor of Engineering, Master of Engineering, and PhD in Mining and Geotechnical Engineering. After completion of my PhD, I started a new position as a postdoctoral fellowship at CFM, so University of Southern Queensland, in just 2023. So my research area is mainly focused on ground supporting systems as well as engineered materials for this application, and also sustainability in geotechnical and mining application. I really apologize if there is any noise in background. I'm sorry for that, but so it is not under my control. So here you can see my email address. So happy to collaborate. Just reach me out if you have anything, any idea or questions. So then we can discuss. So just sorry. Go. Oh, I don't know. But anyway, so let me just touch a bit on background of the problem. So when we construct an underground opening, so we alter the geotechnical and geological conditions, and then the stability of these underground openings may be influenced. So the instability can be due to many factors, such as, just existing of like weak layers, as you see here, or discontinuity. So the density of discontinuity affects the problems. And also, even if we don't have any discontinuities or any weak, layers, so the instability can be due to the redistributed stresses around these underground opening. So what we can do, we need to improve the stability of these openings. So we have different approaches by which we can improve these stability. So mainly we use ground support system or reinforcing systems. In this session, I'm going to talk about the reinforcing approaches. So how we use what is the reinforcing system? So reinforcing systems consist of many different, elements, but mainly we call it rock bolt, cable bolt, or ground support systems. So what is rock bolt? Rock bolt is just simply a deformed bar, but when that we put it inside a hole in the ground. Then we encapsulated these elements and then fill up the hole, the gap between the rock mass and these reinforcing elements. So we can use different encapsulation agents, such as cementitious grouts, which is very common in civil application, and resin, which is very common in mining applications. So so when these elements are installed, so these elements can different types of loads and deformation can apply on these elements. So we can have axial, depends on the movement of the unstable rocks. So we can have tensile load, torsion, or shear, or also can be just a more complex, which is the combination of all these sort of loads. So in this session, I'm going to focus only on the axial effects of these axial behavior of these elements. So when we apply axial load on these elements, the failure can occur in different areas. If this can be on the reinforcing element itself due to the rupture of the bolt, or on the bolt grout interface, on the ground, on the rock mass as well. By the way, so these elements can be made with by different materials such as steel or fiberglass or carbon fiberglass. So I'm not, I don't want to just to talk about these materials. I'm just talking in general. So different factors can affect the behavior of these reinforcing elements. These can be the mechanical and geometric characteristics of these elements itself, rock mass quality, bonding material property, and confining stress and temperature, and underground water as well. So in the literature, if we go to the literature and review the literature, we can see that so since 1980, the effect of confining stress has been acknowledged by many researchers, but basically they have assumed that so these stress is in a hydrostatic condition. But when we install the reinforcing system in the reinforcing element in an underground application like a urban tunnel or mining or whatever it is, so basically we have stresses around these elements with different magnitude and different angles. But basically, we consider in engineering, rock mechanic engineering, so we consider three principal stress around a reinforcing element. This is called sigma 1, sigma 2, and sigma 3. This effect has not been considered in the previous studies, but in this study, in this specific study, we put step forward to see what is the real effect of these stresses if the magnitude is different in different angles and different angles. So what we did, we we prepared some samples and conducted a push-out test using a true triaxial testing machine. You can see in the right side. So in this machine, so we have a chamber and some arms by which we apply load with different magnitudes and in different directions. Okay, so for example, here we have y axis, x-axis, and z-axis. In the y-axis, we have the sigma 1. In x-axis, we have sigma 2, and in the z-axis, we have the push load. So we prepare samples, put in the chamber, apply load with different scenarios. In this scenario, we consider different principal stress ratio. What is different principal stress ratio? The ratio of sigma 2 over sigma 3 is called, that principal stress ratio. We consider the K equals to 1, 1.5, and 2. So with different stresses ranging from 2.5 MPa all the way to 20 MPa, which is sufficient for studying and analyzing this effect of the stress ratio. So we came up with really interesting results, as you see in these graphs. So for example, when we don't have any confining stress, so for these specific samples, the bearing capacity was measured around 27 kilonewton, but when we increase the load, so we had different bearing capacity. So in this figure, you can see a hydrostatic condition where we have the equals identical sigma 2 and sigma 3 from 2.5 to 10 MPa. So in this one, we have a principal stress ratio equals to 1.4, and this one, the principal stress is 2. So we realized that, so by conducting different tests, we realized that when the stresses equals to the confined stress is set to sigma 2 equals to 20 MPa and sigma 3 equals to 10 MPa, we have the maximum bearing capacity, which is about 45 MPa, which is around 100% more than around just 100% more than when we don't have any confining stress. So this is almost equal to when we have sigma 2 equals to 15 MPa and sigma 3 equals to 10 MPa. So these are very important in terms when we design a supporting reinforcing systems and stability of underground, opening. So we also considered and analyzed the bond strength in these scenarios. So, the bond stress is due to the interlocking and the cohesion between the bolt and the encapsulation agent. So here you can see the results in this specific diagram. We have sigma 2 in the horizontal axis and the bond stress or strength in the vertical axis. In a specific sigma, sigma 2, we realize that by increasing the principal stress ratio, the bond stress or strength decreasing. Also, interestingly, we realize that when in a specific sigma 3, for example, when it is 10 MPa, when we increase the sigma 2, then we see a plateau here. This is very important. Why? Because it shows that, for example, when in an underground, we have, for example, 50 MPa or 60 MPa of stress, which is really high. So then we shouldn't expect more or higher bonding strengths. We also analyze the displacement and the strain which occur due to the movement of these bolts that I'm not going to talk about because it would take longer. So we also analyze the cracking and failure modes of these samples. We realize that they stress values and the magnitude and the direction affect the failure mode. For example, in this figure in A, so when we have a lower amount of stresses, we see cracks in the almost in all angles X and Y, and also in the grouting and encapsulation agent as well. But when we increase the stresses, confining stresses, so we see just small and tiny cracks on just rock mass or the surrounding rocks. Also, we slice the sample and we realize when we don't have, any stresses, so the failure is due to the dilation or splitting of the sample, which is obvious. But when we increase the load, we realize in addition to the shear of failure, which is occurred in the bolt grout interface, we also have some damage as well. This is why when damage reaches to a specific amount, so after which we don't have increase in the bonding strength of the bolt. So one of the important aspects in application of reinforcing element in underground application, a critical embedment length. What it means? It means that for this specific bolt, what would be the critical minimum encapsulation length? So we prepare some sample with different embedment lengths from 100 millimeter all the way to 400 millimeter with different bonding materials, including A and B. A is a cementitious and B is a resin. We cast concrete with the UCS of 60 MPa and encapsulated our samples and carried out the pullout tests and to see what is the embedment length and the effect of, for example, bonding materials on the critical embedment length. As you see the diagram here, by increasing the embedment length, we have higher bearing capacity or axial capacity. But comparing these two, we see that the type of bonding agent also affect this behavior as well. For example, for type A encapsulation agent, we see that they because when the encapsulation length is over 300 mm, so here we have the bolt rupture. It means that for this specific bolt, for this specific surrounding rod, and this specific grout, which is A, so the critical embedment length is around 300 millimeter. So we carried out the same thing for resin as well. But here we realized that we had just bolt rupture for the sample with 400 millimeter of embedment length. So we had the bonding of the sample B3 with the 300 mm. So by analyzing the result, we realized that we determined the embedment length for both of these samples. Realized, for example, for the bonding agent A, the critical embedment length is around 250. For the agent B, bonding agent B, the embedment length is 268 mm. So it shows that, generally speaking, it shows that the embedment length is influenced by not only the bolting and the inserting rod, but also is affected by the encapsulation agent as well. So So to do more analysis, we instrumented our samples using strain gauges on both sides of bolt. We made a groove on the bolts, we machined them, installed the strain gauges. Why? Because, for example, in this graph, we see just the total behavior of this bolt, but we know that, so the behavior of these, the bond distress along this encapsulation length is different. To be able to analyze these data, we need to analyze the strain behavior of this deformation and elongation of these bolt along the encapsulation length. To do this, as I said, so we instrumented our rock bolts. So similarly, we installed in the same type of concrete, carried out some pullout tests, and analyzed the data. So here we have different diagrams, which may be confusing a bit, but generally speaking, what we have in the vertical axis, we have interfacial bond distress. Interfacial means the interface between the bolt here, the bolt and the grout, okay, or the encapsulation agent. So we have again 3 different encapsulation lengths, including 100, 200, 300, and 400 millimeter. So what is interface? How we could calculate these interfacial bond distances? This interfacial bond distance is calculated by considering the strain values we got from those strain gauges that we installed along the encapsulation lengths. The difference between these strain gauges, strain values, can give us the interfacial bond stress. So if I just touch this one, so here we see that we have a concentration of stress on both 0 to 50 millimeter. So this 0 to 50 millimeter or 50 to 100, these shows the distance from the free end, which is here. For example, this one is 400 millimeter. So just generally speaking, so this distance is from the free end. So for the 100 millimeter and 200 millimeter encapsulation lengths, we see that we have a concentration of stresses on both area, which is 0 to 50 millimeter and 50 to 100 millimeter. There is a correlation between the load, the applied load, and the the induced bond stresses, as you see. But when we increase the encapsulation length, rather than having a concentration on the amount of interfacial bond stress, the bond stress distributed more evenly, as you see here. But interestingly, for 300 and 400, as you see here, when the displacement of the bolt reaches around between 50 to 20 millimeter, we see the bonding here. But after that, we don't see any debonding till reaching the ultimate bearing capacity. So it is very important in terms of, you know, the designing of our materials. So also here we have some diagrams showing the embedment length and the bond stress, considering the different levels of pull out. So for example, in the 50% of the peak, we see this red line shows that, so the maximum bond stress is 50 millimeter inside the bolt, rather than having it in the exactly on the free end. This also shows that here, this part, let me just go back. For example, this part has been already damaged. But when the applied load reaches around the residual, you know, amount, residual is here, okay? This area is residual, is called residual. So when it reaches the residual bond stress, so the maximum bond stress can be seen in the free end. Similar thing is always in the other samples as well. For example, here, the maximum shear stress at the 50% of the bolt is seen in the area 150 millimeter to 200 millimeter. So in the literature, mainly it is you can see that it is said that, so the main factor affecting the bonding behavior of the reinforcing elements is the UCS of the grouting material. But by conducting some tests, we realize it is not only the only factor that we should consider. We need to analyze more to see what exactly contribute more on this behavior. So by developing some analytical models on the fully grouted rock bolts, we realize that rather than compressive strength or shear stress or tensile stress, or for example, elastic modulus or Poisson ratios of these grouting materials, shear modulus of the materials is more effective. So, for example, here I just draw two graphs using these equations to see what is the effect of shear modulus of on the behavior of these fully grouted bolts. So here we see that we have two different types of, you know, encapsulation agent, including A and B. A has higher shear modulus. This graph also shows that, so when the shear stress at a specific distance from free end, the bolt or the grout with higher shear modulus has higher bond strength as well. So we also wanted to know what is so between the compressive strength, shear strength, and as well as the tensile, which is more effective. So we conducted more tests using different types of encapsulation agent. So with different properties like G1, G2, G1 and G2 are cementitious, while R1, R2, R3 are the resin that you can see here. So we realized that there could be a correlation between these, you know, properties and the bonding behavior of the rock bolts. So by statistical analysis, we realize the coefficient of determination for example, the compressive strength and the pullout, ultimate pullout load is around 94%. For tensile strength is around 45%. However, for the shear strength is 99%. This means that the tensile strength of the bonding agent has the minimum effect, or has less effect on the bonding behavior of fully grafted rock walls. However, the shear strength, and also is follow up on previous slide, the shear modulus has the most effective factors. So we also analyze the failure modes of these samples as well. We realize that for the materials with the higher mechanical property, rather than having the radial cracks, we see some cone shape of failure on the surrounding rock. This is mostly important in civil engineering rather than mining. So we also slice our sample, and we could correlate correlate some relationship between the type of the bonding agent and the cracks and the failure modes of the failure modes of the bolt grout interface. For example, in this figure in A, we see that so we have minimal damage on the bonding agent. However, for example, in figure C, we see the bond is almost completely sheared off. Also, we could see and we could detect some micro cracks on the grout and rock as well. So in terms of the effect of the rock mass on this, sorry guys, I know there's a noise in the background, but yeah. So in terms of the effect of surrounding rock quality on the behavior of bolting system, we realized that we developed some analytical models. We realized that we have two main factors, including the radial stiffness of the rock mass, as well as the compressive strength. So higher radial stiffness has higher ultimate bond strength. Sorry guys, just give me a second. Sorry guys for the interruption. So as I said, so we realized that so we have a radial we have main factor affecting the behavior of this the behavior of fully grouted rock ball, which includes the radial stiffness and the compressive strength. So in this graph, you see for example, we have concrete with the UCS from 20 MPa all the way to 60 MPa. So for example, here you see that in the vertical axis, we have the ultimate bond stress, and here we have displacement. Comparing the result shows that higher compressive stress gives higher bond strength as well. So all right. So another topic is the effect of temperature and the environmental condition on the on the behavior of the rock bolts. Why? Because in the presence of, for example, combustion or fire or in emergency condition, we need to realize what would be the effect of these, temperature on the behavior of these reinforcing elements. Just imagine in a tunnels, in the urban tunnels, we already have installed these reinforcing element. Then, unfortunately, we have a fire. So what will be the effect of this fire on the stability of these in tunnel? So what we did, we cast some sample using different types of resins. So I'm just going to focus on one type of this resin. So in this resin, we install some thermocouples with different distances. Then we carried out again the pullout test. We measure the true temperature along the encapsulation lengths. As you see here, we have the ambient temperature when the temperature is 75 degrees all the way to 250 degrees. We have different distribution of temperature along the encapsulation lengths. So as you see, the higher the higher temperature can cause increase in the temperature along the encapsulation lengths. But when we, for example, go deep into these encapsulation lengths, the temperature drops significantly. So by conducting the pullout test, we realized that the type of resin can affect significantly the behavior of these bonding materials. For example, here we use bonding agent A and bonding agent B. We increase the temperature from ambient to 250. For example, in these specific type of resin, the maximum pullout bearing capacity for the ambient temperature is around 100. For the other resin is around 140. When we increase the temperature to 250 degrees Celsius, so the pull-out capacity decreased to around 60 MPa, and in another resin it decreased to 80 MPa. All these data shows that we need to consider, the effect of temperature and the environmental condition when we design any reinforcing systems. So I think this is the end of my presentation.